And today I'm going to talk about automated machine learning, the past, the present, but also the future. What can we expect in the coming years, and what are cool research directions to go into together as the automated machine learning community. So first of all here, we see an image of a very famous object recognition competition. We see here how machine learning models have been able to perform over, well, it's already a little bit of an old image. Probably it would go further. I don't have a pointer here. It would probably go further if I had found a newer version of this image. But what you can see here is that machine learning models have become better and better over the years at doing tasks such as object recognition. And at some point in 2015, for the first time, the human was outperformed by a neural network. And of course, neural networks are great. We know that neural networks nowadays can achieve state-of-the-art performance and can do really amazing stuff at many tasks, both in predictive AI and in generative AI. We've of course all seen the disruptions that ChatGPT have brought to us, both positive but also sometimes questionable. But training such a neural network is not easy at all. One of the questions here, I took some random image from the internet. This is a ResNet. One of the questions is what type of network architecture do we want to use, and what type of how many layers does a neural network need to have in order to perform at a given task? How wide should the layers be? What activation functions do you want to use? These are all questions that I myself would not be able to answer quite easily, especially when I'm confronted with a new task. So machine learning models are able to perform pretty well at many tasks, yet at the same time it is extremely hard to apply models such as neural networks. And in order to address these challenges, automated machine learning has come into play, where we're trying to develop methods and toolboxes that make training complex models such as neural networks easier for the human. Not to take the human out of the loop, but in order to assist the human in the machine learning loop so that he or she is able to spend their time on more useful tasks than optimizing how many layers, the layer width, and what type of activation function a neural network is going to have. And that's what I hope to talk about today, automated machine learning, and what are some basic principles in it. So training neural networks is hard, and then of course one of the easy things that you could do is you can take a neural network and apply it just out of the box, even on many websites, such as on many websites we now have standard pre-trained neural networks, and you can of course apply them and fine-tune them to your task. That's of course the basic case. There no automated machine learning is involved. But one thing that is already a little bit smarter than that is you can search over various architectures, for example a ResNet 18, ResNet 34, and try which of these architectures eventually performs best in your use case. That's already a little bit more intelligent, but maybe there's more things we can do. You can even tune hyperparameters per architecture. All the architectures, as said, have certain hyperparameters, such as the learning rate, many other things, such as the learning rate schedule. Will it evolve over time? And eventually, what the hope is that at the end of this week, many of you will be able, or maybe are already using automated machine learning toolboxes, but also understand how they are working. And automated machine learning toolboxes that automatically optimize both the architecture of the neural network and its hyperparameters. So why is automated machine learning interesting? Well, I think there's many reasons for that. First of all, it's an emerging research field, heavily invested by various big tech companies, Google, Microsoft, Facebook, Amazon. Many of our students have ended up at those companies already, and those companies are still very committed to invest into automated machine learning. So this is still a field in which good job opportunities are coming forward. And I think it's very important because machine learning in itself can be pretty tedious, and also there's many tasks that are to be executed there. It's good that we do democratize the access to machine learning expertise by allowing automated machine learning techniques to help machine learning experts. And one reason to also use automated machine learning is by not using it, it's just too annoying, right? To check for a given data set, first try a first architecture, then try a second architecture, then try a third architecture. It's just something you don't want to be involved with. I have been involved with this many, many years before, and I can tell you this is not something you want to do. This is already, if you once have optimized the hyperparameters for a machine learning model yourself, you know immediately why this is a job not for humans, but for machines. And eventually, as I said before, it's there to support the data scientist, not to replace him or her. Now, let's then go a little bit deeper into what is automated machine learning. Automated machine learning can largely be divided in three important components that all have their own interesting research directions. And the first component is the search algorithm. And the search algorithm kind of determines for a certain problem what kind of configurations we are going to try. After a certain neural network has been applied on a machine learning data set, how are we going to try some other configurations based on this first try? So search algorithm kind of guides the search, and we will look today at various options, random search, grid search, Bayesian optimizations, and more elaborated versions of those. Second component is the search space. The search space basically tells you which hyperparameters are we actually going to search over. Are we going to look at a certain amount of layers? What is the width of such a layer? What is the activation function? Which hyperparameters are important is then, of course, an important question. How to sample from those hyperparameters and what ranges are we going to explore. With learning range, you could say maybe we start at 10 to the power minus 5 and we go until 10 to the power minus 1, but who has come up with those ranges? And do they make sense, or should we extend them? Should we make those ranges smaller? All these kind of considerations are important for doing research towards the search space of automated machine learning. And next, the third component is about the evaluation mechanism. And the evaluation mechanism basically says, if you are going to try out many different configurations, so we're going to try eventually many different types of neural networks, which of those is eventually the best? Which should we pick, and how are we going to determine which of these we're going to pick? And those are all things that we talk about when we talk about evaluation mechanism. And then when you take all these components together is what you get automated machine learning, and there are many prominent examples of those already. Auto-scikit-learn, Auto-scikit-learn 2.0, AutoWeka, basically all your favorite machine learning toolboxes nowadays have typically also an automated machine learning component to them that help the data scientist in automating some complicated problems that they can encounter when using them. So what are we going to discuss about these components today? Today I want to go a little bit into all these three components and into the combination of automated machine learning. I want to discuss the basics of all the automated machine learning techniques. One thing I like myself a lot about automated machine learning is it's not super complicated, the basics. It has some pretty neat mathematical basics, but the basics are quite easy to understand. And the moment you're able to understand the basics, it's pretty nice to reason about certain ways how would you do things better if you were to do an automated machine learning algorithm. And I hope that that would be the goal of this week, right? How to add to the, understanding how to add to the basics of automated machine learning and come up with even more advanced algorithms, either for search algorithm, for the search space, or for the evaluation mechanism. So that's what we're going into during this presentation. Now let's start with the problem definition of automated machine learning. Who has already read automated machine learning papers will probably have seen something that either looks exactly like this, or that looks very similar to something like this. And automated machine learning, the hyperparameter optimization problem is typically defined as follows. Given a new data set D that you can then split up in a train and a validation set, and later we go into a little bit more detail what is such a validation set. It's not the same as a test set, but we come into that in a second. What is and an algorithm A, for example, a neural network, given a search space lambda, that search space we also talked already about, and we will also go a little bit into more detail later. What is the hyperparameter configuration, small lambda star, that optimizes a given loss function? And the loss function here is defined over the algorithm with the hyperparameter configurations that is trained on the train set and then evaluated on the validation set, probably using some evaluation metric that you're interested in. Maybe that can be accuracy, maybe it can be error rate, which is of course the inverse, or area under ROC curve. Basically what you're interested in. I see a question from Marius. My name is, I will find a new name tag in case you forget my name, just Jan or John is fine, so I'll leave it out here for now. Thanks, Marius. And so this is the hyperparameter optimization problem. Let's make this a little bit more complicated, because that is what automated machine learning often addresses. Here I talked about a static algorithm. Automated machine learning often says, hey, we're not just interested in a static algorithm A, but we also want to know if you're going to use a scikit-learn algorithm. Typically, I don't say beforehand, I want to use a support vector machine, or I want to use a multi-layer perceptron. Typically, automated machine learning is all about which algorithm and which hyperparameter configuration should we take. And again, then the problem definition looks very similar to what we've seen before. In this case, we have a set of algorithms, capital bold A in this case, again, hyperparameter configurations, capital lambda, and what we want to do is we want to find both the algorithm and the hyperparameter configuration that optimizes this same loss function. And many of the problem definitions that you will see in the papers that you're reading either look exactly as this one, similar to this one, and this is the one that I took from a paper from 2012, one of the first real automated machine learning systems that I myself am aware of, but that many of these things look quite similar. Now, how do you go basically from a hyperparameter optimization problem to an automated machine learning problem? Suppose that you have one way of doing this is by reducing the hyperparameter optimization problem to by reducing the combined algorithm selection and hyperparameter optimization problem to a hyperparameter optimization problem. And suppose that we have two algorithms, maybe a random forest and maybe a neural network, and both have a set of hyperparameters. Basically, we combine these hyperparameters together in one big hyperparameter configuration space, and we add one hyperparameter that basically tells us which algorithm we're going to pick. And then you have the sum of all the hyperparameters of all the algorithms plus one. That's the amount of hyperparameters that you're essentially optimizing. And that's one way of addressing this combined algorithm and hyperparameter optimization problem. Good, so these are the problem definitions that we're going to look at, and automated machine learning addresses many more problem types. And maybe you've heard of neural architecture search, and maybe you've heard of few-shot learning and meta-learning. Those are things that we, not in this presentation, will touch, but I'm sure that this will all be part of the curriculum of the rest of this week. But today we will focus mostly on this combined algorithm selection and hyperparameter optimization problem. Now first, let's go into the machine learning pipeline. We've already said machine learning is all about solving data science problems, and maybe, would there be a way to get a pointer out of this, Marius?
Unfortunately, yes.
Okay, it seems to work. Okay, good. Maybe we have somewhere a handwritten digit. In this case, someone has written 5 on some sort of paper, and we want to classify this handwritten digit as the real output that we're interested in this case 5, and originally we're interested in employing a machine learning framework for this. And again, machine learning framework can consist out of a data preprocessor, a feature preprocessor, a classifier, and when you use scikit-learn, then you can already see there are many different classifiers that are able to solve this problem, many different hyperparameters. The feature preprocessor, the data preprocessor, all things that we need to optimize, and these are all questions that we need to address. Now, one way to address this is by looking at it as a black box optimization problem. So we have the input, that is X here, or data set, that goes into some black box. Here the black box, the machine learning algorithm is going at play, and then out comes some output, for example, the predictions on the aforementioned validation sets. And typically what happens is you can make a loop around this, and the question is, suppose that we have some output, we have some predictions evaluated, then we want to make a new decision on what to do next. Maybe we have tried just a neural network with a ReLU activation function. Maybe the next decision is going to be a neural network with a YeLU activation function, or whatever next step you're going to try out. And one way of addressing this is by doing grid search. Very simple approach. We just take various hyperparameters. In this case, we have selected 2 hyperparameters. We have splitted them up in a certain grid. We have taken several values on the grid, and we're going to evaluate all these individual values, and eventually we look which one of these is the best. Now, this is of course not a very good approach, and one thing that we figured out since 2012 in this paper, it lays it out pretty nicely. Grid search has one big problem that might not be extremely obvious, but the moment that you have, in this case, a very important hyperparameter, maybe this is the learning rate, and I've also made a mistake, I've also added a not so important hyperparameter to the grid, and maybe I just, by accident, I didn't know what a logging hyperparameter was, and I'm just adjusting here the logging threshold. Actually, now I'm wasting a lot of compute power, because this hyperparameter here displayed on the y-axis doesn't influence the performance of my algorithm so much, but still I'm using 3 times the budget in this case that of what I should have used, and this is of course quite wasted. So in this case, we see here would have been the optimum. We're missing out on this optimum just because we're wasting computational cycles. Additionally, also, of course, if I would add now a 3rd hyperparameter, I cannot really maintain this 3x3 grid, right? Because then I have 27 configurations, then a 4th hyperparameter would add more to it. So there's a certain limit to things that I can do when using grid search. So bottom line, we don't use grid search so often anymore. Similar for random search. Random search, also a very simple baseline, very easy to implement, good to study the problem. Of course, definitely not state of the art, definitely not what you came here for to this automated machine learning school. But random search already performs better than grid search, because I made here the same mistake. I've chosen a hyperparameter that is quite important and a hyperparameter that, again, is not important at all. And due to the way that I now completely randomly have sampled configurations, it does not look neat or organized at all, but I no longer have this problem that I miss and that I waste configurations on this unimportant hyperparameter. And now I've actually, because I completely let go of the original grid, I have solved the problem that I am wasting configurations in a certain dimension that was not good for us. So random search, while this is not the state of the art, and this is definitely not something that comes close to current state of the art methods, it already has some very nice properties that we can exploit in more complicated methods. But still, of course, random search, the more hyperparameters you have, the harder it will have a pretty hard time to find good regions in the search space. Now, what is then one of the state-of-the-art algorithms. The state-of-the-art consists out of many different algorithms, but one of the state-of-the-art algorithms that you should definitely be aware of is Bayesian optimization, and we will dive a little bit deeper into Bayesian optimization in the next slides. And here we have an image where we are going to optimize the configuration space, and here I only visualized one hyperparameter x. In this case, we're optimizing an objective function f of x, and well, let's imagine that we're optimizing the error rate. I want to have as few as possible errors in this search space, and basically I have already randomly gathered several observations. And we see here that if I had value -10 for this hyperparameter, I had a pretty bad response. I had 16 mistakes. Here, close to the 2 mark, I had only 1 mistake, and here I have 1.5 mistakes. So we have already some observations measured. Random search itself would now just completely ignore this information and send them randomly somewhere along these axes. With Bayesian optimization does something a little bit more smart. It says, what if we train a regression model to predict for all the points that we don't know yet how good it will perform. And if you do that, you will see something very similar to this. Here, probably a Gaussian process regressor has been used to train this objective function. And we see here that it nicely fits the data points. And now we have at least some sort of guidance that I know I don't want to sample data points in this region, and probably I want to sample data points in this region. So that's already something that helps us move towards the good regions in the search space. Now that's of course a very vague idea. I want to have this a little bit more formalized. Now, which point should I actually take? Do I take something close to this point? Do I take something further away from this point? Do I take something exactly in the middle? I don't know. That's not something that I determine myself, but for that we typically use something that's called an acquisition function, and we will go a little bit deeper into the acquisition functions on the next slide. But this acquisition function basically takes as input the prediction of the Gaussian of the probabilistic model, both the average and the uncertainty that it gives us, and basically based on whichever acquisition function you choose, then of course you can have a very greedy acquisition function that exploits things. You can also have a more explorative acquisition function, and based on the acquisition function, a certain utility for every next value will be calculated. And in this case, the point here exactly in the middle is determined to be the most fruitful point to try out next. And what we do then is we take that configuration, we run our machine learning algorithm with that certain hyperparameter value, and after that our model is more knowledgeable, and we will be able to steer the search procedure even better. And here we also see the real optimal value in the dashed line, but that's something you of course never know in practice. So what type of surrogate model should we take? Well, generally there's 2 or 3 models that are used quite often in the machine learning community. Either a Gaussian process, which has very nice confidence bounds, or a random forest, which works very nicely out of the box and quite often doesn't have to optimize its hyperparameters to get nice performance on the regression task, and often trained or always trained on the initial points of your search grid, what you've already tried, and you update it every time after you've gotten a new point. And then the question is, what about the acquisition function? Well, also here are various options. Often expected improvement, the upper confidence bound, or entropy search are being used. And here we see an example of expected improvement, which looks in itself quite complicated. We see here, did I use the right? Yeah, I did use the right formulation here. We see here some complicated symbols, but when you all put this down into Python code, things don't look as complex as they seem. And this basically takes as input both the x point, the prediction of your the average prediction of your probabilistic regression model, and the uncertainty bounds And as a result, it gives you the acquisition function or the acquisition value of a certain input value, which is the green line that we saw on one of the previous slides. And if you then visualize how Bayesian optimization would work a little bit, this is the outcome of some Bayesian optimization run that some Stack Exchange user uploaded in the year that I for the first time gave this type of lecture. Then you see that the good area is typically the redness of the background here tells us, we see here two hyperparameters. The redness of a point here on the background tells how good a certain point is. The real optimum is something here, although we will never know what the real optimum is in a realistic setting. And basically what you see is that after some initial exploration, Bayesian optimization does predominantly find that it needs to search in the good regions. So this is the basics of what is used in many automated machine learning toolboxes, some form of Bayesian optimization or some advanced form of random search. Now let's look at some ways of how can we make this a little bit better. And one way of making Bayesian optimization perform better is Bayesian optimization often starts with some random data points in itself that does not seem extremely smart. And what you can, of course, do is you can try to figure out if you've seen already previous data sets. You can already see if you, once you've done many machine learning runs on the previous data sets, you can see if you can learn certain features that generalize across those data sets. So for example, you could try to deduce if you have a data set with only few data points. Maybe you've already seen many other data sets with very few data points, and maybe we can induce from that in this case we should use maybe a linear model, or maybe we've seen some patterns in the previous data sets. And this is called meta-learning. That's something where we released 2 years ago an open access book on, and when the slides are available online, you should be able to click on this slide and go to this open access book. So meta-learning is one way to further improve Bayesian optimization. Matthias, who just came in, was one of the first persons to do this. And this is a very cool way of improving the performance of automated machine learning methods. Another way, what I think is a very cool point of research, is what Sversky et al. Did in 2014. Basically what they said is, well, you can, on top of a current data set, we can of course learn the probabilistic model just over one data set, but we can also create some auxiliary tasks that are basically the data set, but then on a smaller amount of data. And we can basically train the probabilistic model over all these different data sets together. And then you don't always have to sample on the large data set, but if there's some correlation between the auxiliary task that you create and your original data set, then this will help you do things faster. So this is also a very cool way of improving Bayesian optimization and making it faster than it is already. Okay, I think I also do have to hurry a bit, but let me continue with the second component, the search space. And this one I will go through a little bit faster. So we've talked so far about the search algorithm. So how are we searching the search space, but what is this search space that we are searching through? And the way that I like to think about the search space myself, there's not extremely a lot of research going towards search spaces, but the way that I like to think about search spaces is you open the documentation of your favorite machine learning algorithm, and basically you look at all the hyperparameters that are either listed there or that seem important, and then what you are going to do is you're going to define some reasonable ranges over that. And that is a little bit more of a dark art than something where is a lot of pointers in literature towards. Here we see the scikit-learn MLP classifier, clearly not the MLP classifier you want to use, because if you use neural networks, typically, of course, you use TensorFlow or whatever, but this gives a nice idea of what type of hyperparameters are available. And the type of hyperparameters that exist and typically are categorical. For example, think of an activation function. And these are kind of complicated hyperparameters to deal with because there's no notion of a distance between certain values quite often, right? So you have, or at least no natural notion, you have to define it yourself. You have the ReLU activation, the GeLU activation. What's the distance between those? There's no average between those, opposed to, for example, numerical hyperparameters. So if you take the learning rate and you say, okay, we have a learning rate, we can put it to 10 to the minus 5 and 10 to the minus 4, and there's a clear difference in between those values that you can take in such a way that you can assume that a small change in your input space will also lead to a small change in the performance. At least that's what we're hoping, right? We hope that the performance landscape is a little bit smooth, and if not, then, well, some of our algorithms will have a hard time latching on. It can also be an integer. There can be conditional hyperparameters. Some hyperparameters are only relevant when another hyperparameter is set to a certain value. And basically a question then how to encode such a configuration space. And to the best of my knowledge, one of the only packages for this is the config space package, which in this case I tested out some config space that came from AutoScikit-learn with config space version 1.2.0, and then with some minor lines of Python, you can basically define all things that are relevant for such a configuration space, including which hyperparameters are you going to use, which ranges, what are the default values, and in some cases you can even define what is your sampling strategy. Do you want to treat all values equally likely, or do you have a feeling that in small values, that the difference between small values is more important than the difference between large values? In this case, you can put them on a log scale. Now, of course, then one interesting question is what hyperparameters are important, and this is some work that we did in 2018, or let's first look at how can we assess what are important hyperparameters. And well, here we see the concept of a marginal. One way when I was a PhD student, the first thing I thought, how can I assess what is an important hyperparameter? What I did is I just took different values for a certain hyperparameter and I tried to plot a hyperparameter development curve, so to say. Well, that's clearly not what I want to show here. What I'm showing here is the marginal, which is a very complex concept. And the marginal basically tells us, for each point on this curve, on this marginal curve, this average basically represents, if I set this hyperparameter to this value, what is the average expected performance averaged over all other hyperparameters and averaged over all values of all these hyperparameters. So that's quite a complex question that might not be even obvious how to calculate this, but I'm not going into too much details, but the work by Frank Hutter from 2014 tells you how to exactly make this complex calculation with some assumptions. That's called functional ANOVA, and that tells you also then for each hyperparameter what is the contribution to the variance in the performance landscape. And what you then can easily assume, here we see two hyperparameters that do have quite some effect. There seems to be quite some variance in the marginal, which basically means I really want to optimize these hyperparameters, because if I don't, then I might actually miss out on a good performance value. Whereas if the marginal would look pretty smart, then, or pretty flat, then it doesn't really matter how to optimize the hyperparameters. Yes, and this is something that another project that I worked on comes in pretty handy. AutoML.org is a website where we try to gather many machine learning experiments and the results of those experiments, and basically this can be used to feed into these type of mechanisms. And then what are important hyperparameters when you measure it over many data sets? For here we did it for the support vector machines in 2018. There we turned out that exactly what you expect are the important hyperparameters: gamma, complexity, and the combination between those two. And you can also do this for example, REST nets, but even for quantum neural networks. And then what comes out, hopefully, is things that confirm what are the important hyperparameters that are your intuition, but also in many cases, interesting new patterns come out. And I believe that Marius and his team even have work on hyperparameter importance across multi-objective hyperparameter importance, which is also very cool work. And I will ensure to add the reference to this slide. Good. That was the search space. Let's then go into the evaluation mechanism. And we've talked already a little bit about things like a train set. Of course, you all know about a train set. And when you use machine learning, you also use a test set quite often, because you want to measure generalization, performance. And in machine learning, it's quite easy to work with a test set because you have maybe a neural network, you apply it on you train it on your train set, you test it on your test set, and then you know how well it performs on unseen data points. Now, with automated machine learning, what we're doing is actually we have multiple configurations that we are going to try out. So maybe we're going to try out a neural network with 10 different layers, with 20 layers, with ResNet 36 layers. And one thing that could be a mistake that we want to avoid is we don't want to use the test set multiple times. If we're going to use the test set multiple times, then we have two problems. Problem one is we're basically violating any assumption of machine learning. In many cases, you cannot test the test set multiple times. Imagine me being a company giving you a data set I want you to develop a method on. Of course, I'm keeping the test set for myself behind. So basically, to test whether what you come with yourself is pretty good. So the test set really is typically a one-shot approach. And if you are using the test set multiple times, you are basically also that lead to overly optimistic performance estimations. So what are we going to do there? Usually we have a data set that is split into a train and a test set. The way to solve this is quite obvious. We're also going to split the train set then again into what I would call a real train set and the validation set that we've already seen several times during this lecture coming through. And what we're then going to do is we're going to 200 times or 1,000 times or as long as our budget allows, we're going to train different configurations on this smaller training set. And then we're going to validate it on this validation set. And the one that performs best, that's the one that we give back to the person who gave us the assignment. And that person can test it on this test set. So this is one way of getting less biased or actually of avoiding violating this, how do you call it? This assumption this rule basically that we can only apply the test set, that we can only see the test set just once. And so now we have evaluation both at inner level and at outer level. And at inner level, basically, we are assessing the performance of a certain configuration. And at outer level, we are assessing the performance of our automated machine learning framework altogether. And of course, now we have even less data to perform or hyperparameter to train our individual configurations on, but that's the price we're paying. And that you can also solve, by the way. Once you have gotten your best configuration, what you can do is you can then train it on the original train set, and then you basically have your configuration back with original amount of data. Now, does this solve all problems of bias? Not really. So here I've plotted an image that we recently did with a master thesis. And quite often what you will see is that the performance on your validation set will be higher than the performance on your test set. That's just something quite unfortunate in many cases. And here in the master thesis, one of our students basically actually illegally run, in this case, 1,000 configurations, all illegally tested them also on the test performance. And basically what you then see is you will see some performances. All point in this plot is a configuration, both evaluated on your validation set and evaluated on your test set. And basically what you then will see is sometimes your test score will actually be higher than your validation score. Sometimes your validation score will be higher than your test score. But because we are now optimizing on the validation performance, we will probably pick this configuration, which has a validation score of something close to 0.9. So we score pretty good on validation performance. But the moment that this is the one that we're going to test on the test score, we will note that we will only have 85.5 actual performance. That's just something very unfortunate that is happening, and there's not a lot that we can do about this. There are some methods, but I won't go into detail about that today. The effect can also be mitigated. This effect is especially large when your validation set is small. The larger your validation set becomes, the smaller this effect turns out to be. Maybe a bit of counterintuitive, but the more complex your original data science problem is, if you have multiple classes, it also mitigates this effect in a certain way using multiple validation faults. So internally we can use cross-validation as well. This also mitigates this effect to a certain degree. And one thing that our colleagues in Munich recently figured out is that shuffling the validation and, no, I should have said the validation and train splits, so I will update this in the latest version of the slides. But shuffling the validation and train splits per configuration that you try out. So every time when we try out a new configuration, if we then sample a new train set and a new validation set for that also mitigates this effect. And turns out this effect exists both for simple methods such as random search. Turns out there is a similar effect that makes it even more severe for Bayesian optimization, because random search doesn't do anything smart and it will not latch onto good points in the performance space. Bayesian optimization will even start to find better configurations based on earlier configurations. You see that here, that later in the search procedure, we see the red dots, they occur later in the search procedure. And you see them all here grouped at the top. It will at some point latch onto good points. So the effect for Bayesian optimization is even stronger than it is for random search. Yet, despite this overfitting effect, Bayesian optimization typically performs still better than random search. So this overfitting on the validation set, that's something that's unfortunate, but despite that, Bayesian optimization still performs better. Now, can we further improve this? So we've now seen about how to do an evaluation mechanism, how to evaluate your internal configurations. Now, in one way, you can of course then do what we just talked about, have a train validation split to measure the performance internally. But maybe we can do things that are even smarter than this. So we can even subsample the train set, so that if you have a very large train set, maybe we don't want to train on the entire train set, but we want to train on only a part of the train set. What we can do is we can do this iteratively. We can train on small parts of the train set, but if a configuration seems good and seems fruitful to work on, we can give it even more data, and we can even use certain learning curve models to predict what type of configurations we want to work on. And why would we work with these type of subsamples? Why would we want to be more efficient at the cost? We already said you don't want to subsample the validation set because that leads to, we already saw that leads to a more overfitting effect on your validation set. So why would we want to subsample eventually this train set? Well, because if we are able to faster evaluate our configurations altogether, that means that we can try eventually more. And if you do this in a smart way, then maybe we can do it in such a way that we don't lose too much performance and still choose a reasonably good configuration. And one way to model this is by using multi-armed bandits, which basically are named after slot machines. And every time when you, in a slot machine, you can pull a lever and some output comes out. Of course, in the casino, often you will lose some money, but maybe in the machine learning world, one thing that you can do is you can figure out a way to smartly invest your budget, whatever the budget is, to check out the performance of certain configurations. And one way of doing so is an algorithm that's called successive halving. It's a very easy algorithm. Basically, you give all configurations that you have a certain amount of budget. You evaluate the performance after a certain amount of budget. And after that, you drop the configurations that don't seem good so far, and you give the other ones a double amount of budget. Now here we have still 4 configurations left. We're again going to drop the configurations that don't seem to perform pretty well. And again, we have now an estimation of how good certain configurations perform, giving it more budget. And now we know how well what we think the best configuration is, how well it performs. And this way we only use a little bit more budget, but we are actually evaluating many different configurations. Now this algorithm in itself has some important hyperparameters, the budget, how many configurations are we going to try, how many budget do we give each of these configurations, how are we going to deal with dropping certain configurations, at what type of budget, and how many configurations are we going to try initially. In this case, the algorithm was set up, or in this case I give an example where we have a budget of 384 configurations, and we're starting with 64 algorithms, and this would be a way to then distribute the budget over all these configurations. So I can give them all originally one budget. Now what does one budget mean? You can think of one budget as either one data point or one unit of data points, one epoch. You're giving it a certain training budget. Afterwards, the best 32 get the double amount of budget. Afterwards, the best 16 get again the double amount of budget, until in the end you only have 2 left with 32 budget. But I can also change this a little bit, and I can decide to, with a very similar budget, actually here I have a little bit less, I can distribute it in such a way that I start with 81 different configurations, but now I triple the amount of budget every time, and I remove 2/3 of the amount of configuration. So this is a way to even more aggressively explore more configurations. Now, what type of budget can you use in these cases? So we already talked about observations. You can use runtime. You can give a certain configuration, maybe an hour initial budget, 2 hours, next 4 hours, etc. Of course, your machine learning algorithm should be able to allow for this anytime a model that it should be able to give back. You can use a suitable hyperparameter value. Epochs, you can give it 1 epoch as initial budget, 2 epochs as budget afterwards, or an ensemble size. We train gradient boosting with 1 iteration, 2 iterations, 4 iterations, etc. Or you can even use the attribute hyperparameter, but that, or the number of attributes in the data set. You train it first with 1 attribute, then with 2 attributes, then with 4 attributes. But this is a little bit more tricky than all the others for various reasons I don't have time to elaborate on. So successive halving, very simple approach. This is a way to really speed up the random search procedure, so all the advantages of random search basically come into play. But also, don't forget, this is just an extension to a simplified random search method. And in order to really get nice performance out of it, you would probably have to train some models to combine, for example, Bayesian optimization and successive halving in one way. Good. Let's see how we can even further optimize methods that use subsampling. And one way of doing so is by using learning curves. There's many different models that one way or the other model a learning curve. This is basically what a machine learning curve based on accuracy often look like, and based on some initial data observations. Maybe you've trained a machine learning model until a certain amount of budget. Often you can then fit a learning curve model to predict how it will perform in the end. Many of these learning curve models are available. This is work by Doman et al. That basically tries to fit all these learning curve models together, trains a mixture model of these learning curve models, and uses that to predict how well a curve or how well a configuration works on the final part of on the final budget where you eventually want to try such a configuration. Some other work, I see that the reference fell away. This is work by Sversky et al. Freestyle Bayesian optimization. Basically what they try to do is they basically do Bayesian optimization, but they're also learning the learning curve model based on the Bayesian optimization, and in such a way that after a certain amount of epochs you can also predict, based on earlier learning curves that you've seen on the same data set, how well will a certain learning curve perform, and then if it doesn't look good or doesn't look promising, then you will stop it. And in this case we see all the blue curves do not seem so promising, you will stop it, and eventually a curve that does look pretty well, that will be continued to the full budget. And you can even make some sort of assumptions based on learning curves. So one way that we like to think about learning curves is that they are often convex. So it's unlikely that if you give it a new amount of budget, you give it a double amount of budget, that the performance will increase with even more than you've seen it increase already. Quite often the performance of learning curves, of course it will get better the moment you give it more budget, whatever this budget is, and not always, but it will also flatten down at some point. So quite often you see such a convex learning curve develop. And non-convex learning curves, well, I have to say, you do see them in practice. This stuff does happen sometimes, but in many cases, especially if you have good performance estimates obtained over many random seeds, quite often the learning curves do behave like they are convex. And that's of course also something that you can exploit in automated machine learning. Suppose that we have seen already one configuration that works pretty well, and we've seen the learning curve eventually reach to a certain error rate, in this case somewhere around 5%. And now we are trying to run a new configuration. It would be unlikely that this one, if we extrapolate the performance according to some convex schedule, it would be unlikely that this one would eventually become better than the thing that we have already seen. And this is therefore one of the configurations that we can stop and not waste any further budget on. So this is one way to use learning curves to early stop with configurations that do not seem promising early on in the process. Now those were the three different components. Let's quickly look at what automated machine learning systems could look like. And I don't know, I don't have much time, so I will go a little bit fast over this. But this was one of the first automated machine learning systems that came out of scikit-learn 1.0. Here we see quite a nice image, and basically this brings together many of the components that we have just talked about. It uses Bayesian optimization to search smartly for certain configurations in the search space. It has some meta-learning components. It eventually does something smart with the configuration that comes out of it. We have explored maybe 200 or maybe even 1,000 different configurations before people would throw away everything that is not the best configuration. Well, in this case, a smart method has been used to combine them into an ensemble, some of the best configurations. And that is one of the cool systems that basically have the promise, if you use this system, you press basically the button and a good configuration comes out as long as you give it enough budget. Similar thing exists for, in this case, Keros, AutoKeros, which is more aiming at image classification, builds a neural network based on some smart morphing procedures and some Bayesian optimization procedures. But basically the point that I would like to make before ending this presentation, there's a zoo of automated machine learning libraries out there. And quite often, whenever I give this lecture to my students in Leiden, then the question comes, and now we've solved the machine learning problem, what about the automated machine learning problem? Which of these libraries should we eventually use? Now, the answer to that, what I like to give, what I like to think at least, and which I think also is true, is, well, if you have machine learning and you use the wrong machine learning model or the wrong hyperparameters, you're really paying for this in performance. You will get a pretty bad performing model, and this is something that in many businesses would not be an acceptable outcome to a automated machine learning solution. Whenever you use automated machine learning, and suppose that I use the wrong automated machine learning toolbox and therefore not the optimal choice, quite often I only pay for this in runtime. I will still get, if I know what I'm doing, I will still get a pretty good model that comes out of it, but I just have to wait longer for the good model to come out of it, which I think is a more acceptable solution than having lower performance. So quite often, when dealing with the automated machine learning selection problem, making a wrong choice is not as severe as making the wrong choice on the machine learning problem. Many of these toolboxes have very distinguishing features. They all use the building blocks that we talked about already, Bayesian optimization, multi-armed bandits, meta-learning, stacking, all these cool features that the machine learning and the automated machine learning community have come up with are in one way or another built into these systems, and they combine them all in some unique way. Yes, then what is next for automated machine learning? Automated machine learning clearly is going into a multi-objective direction. I know some labs that are working into interpretable and explainable automated machine learning. I know some labs that are working into making models automatically that are more fair, so that can be better used in the machine learning community. What we are interested in Leiden is robustness of machine learning. So here we see a machine learning model that is quite well at, works quite well, it works perfect at distinguishing these two classes. But we also want the model to be able to robustly assess the difference between those two classes. And one way of expressing this is making sure to measure for us whether all the classifications, if you perturb the input, so suppose that this data point would now be moved a little bit here to the top left, would we still have a good classification? And for certain ways, here we see that the network still is good if we have a little bit of bandwidth around all these data points. If you would look for a larger bandwidth, clearly there would be misclassifications in this case. So this is a way of looking at robustness of machine learning, and that's something that we're very interested in at Leiden University. But clearly there's more ways of multi-objectivity that people currently are looking into. Good, and with that I want to round up. Today we talked about search algorithms, search space, evaluation mechanisms, and all these things coming together into automated machine learning systems. My experience mostly is meta-learning, as mentioned before. The book, Automated Machine Learning for Robust Neural Networks, unfortunately didn't have too much time to talk about that today, but I'll be around approximately until lunch, learning curve analysis, and openml.org. And feel free to ask any questions.